For decades, cosmologists believed they had nailed down one of the most important numbers in all of science, a single value that described how fast the universe is expanding, a rate baked into our deepest models of space, time, and cosmic history. Then, two independent ways of measuring that number started giving different answers. Not slightly different, significantly different. And the gap is not closing. If anything, it keeps getting wider. This is not a minor calibration issue. It is a fundamental crack in the foundation of modern cosmology. Before we continue, if this kind of content sparks your curiosity, subscribe. Because the deeper we go, the more surprising it gets. And most people never hear about what you're about to see next. To understand why this matters so much, we need to go back to where it all started and trace how humanity went from believing the universe was a small dome of stars overhead to realizing it stretches for tens of billions of light years in every direction. For most of recorded history, the cosmos was a compact and orderly place. Ancient civilizations imagined Earth sitting motionless at the center of creation, covered by a rotating shell of stars. The planets, the sun, and the moon all moved around us in perfect celestial circles. This geocentric view of the universe felt intuitive. After all, nothing seemed to be moving beneath our feet, and the stars rose and set like clockwork. By the 2nd century, the Greek-Egyptian astronomer Claudius Ptolemy had formalized this picture into an elaborate mathematical system. Planets moved in smaller circles called epicycles, which were themselves orbiting Earth in larger circles. The system was complex, but it worked well enough to make predictions. And it dominated astronomical thinking for roughly 1,400 years. Then, in the 1500s, Nicholas Copernicus proposed something that challenged centuries of consensus. He suggested that the Sun, not the Earth, sat at the center of the solar system. Earth was just one of several planets orbiting it. At the time, this idea was deeply controversial. It displaced humanity from the privileged position at the center of everything. But the mathematics worked better, and over the following decades, astronomers including Galileo Galilei and Johannes Kepler built on the idea and began confirming it through observation. 2 centuries later, William Herschel mapped the distribution of stars across our galaxy. He recognized that the Milky Way was a vast, flattened disk system, not just a random scattering of lights. Stars clustered more densely toward the center and thinned toward the edges. It was a magnificent structure, and for a while many astronomers simply assumed it was the entire universe. What else could there be? That assumption survived into the early 20th century. Fuzzy patches of light called spiral nebulae had been observed through telescopes for years, and the debate about what they were, island universes unto themselves, or just gas clouds within our own galaxy, remained unsettled. The resolution came in 1923, from one man and one instrument. Edwin Hubble was working at the Mount Wilson Observatory in California, using the world's largest telescope at the time, the 100-inch Hooker reflecting telescope. Peering into the Andromeda Spiral Nebula with extraordinary care, he spotted individual stars within it. Among them, he found a Cepheid variable, a type of star that pulses in brightness at a rate directly tied to its actual luminosity. These stars are like cosmic lighthouses. Because you know how bright they truly are, you can compare that to how bright they appear from Earth, and the difference tells you exactly how far away they are. This technique, known as Leavitt's law, was named after Henrietta Leavitt, an astronomer working at Harvard who discovered the relationship between Cepheid pulsation periods and luminosity after cataloging over 2,400 variable stars. Her work, despite being overlooked during her own lifetime, became one of the most powerful tools in astronomical history. When Hubble applied Leavitt's law to the Cepheid he had found in Andromeda, the result was startling. Andromeda was roughly 900,000 light-years away. That placed it far beyond any reasonable boundary of the Milky Way, which spans only about 100,000 light-years across. Andromeda was not a gas cloud inside our galaxy. It was an entirely separate galaxy, containing its own hundreds of billions of stars. Overnight, the known universe grew by an incomprehensible factor. Hubble continued. He identified 23 more galaxies using the same technique. Some were as distant as 20 million light-years. The universe was not a single galaxy. It was a vast collection of them, each containing billions of stars scattered across distances that the human mind can barely begin to process. But Hubble was not finished delivering surprises. His next discovery would lay the groundwork for an entirely new understanding of the cosmos and would eventually lead to the crisis that astronomers are still grappling with today. Before Hubble could make his next leap, he needed a piece of work that had already been quietly completed by someone else. Vesto Slipher was an astronomer at the Lowell Observatory in Flagstaff, Arizona. Starting in 1912, he spent over a decade systematically observing more than 40 spiral galaxies. He was measuring something called redshift, the stretching of light toward the red end of the spectrum that happens when a light source is moving away from an observer. The same effect works in the other direction. When a source moves toward you, its light is compressed toward the blue end of the spectrum, known as blue shift. Slipher noticed that nearly all the galaxies he observed were redshifted. They were moving away from us, but without a reliable way to measure how far away these galaxies were, he could not determine their actual velocities or draw any larger conclusion. Around the same time, a Belgian priest and scientist named Georges Lemaître was working from a purely theoretical direction. He took Einstein's equations of general relativity and asked what they implied about the universe as a whole. What he found was striking. If Einstein's theory was correct, and if the universe was the same in all directions, what cosmologists call homogeneous and isotropic, then the universe could not be static. It had to be either expanding or contracting. Lemaître proposed that it was expanding, and he even derived his own version of what would later become known as the Hubble Constant. But his paper, published in French in a Belgian journal, largely went unnoticed by the broader astronomical community. In the Soviet Union, a mathematician named Alexander Friedmann had independently reached similar conclusions from the mathematics of general relativity just a few years earlier. He showed that Einstein's original static universe model was actually unstable. The slightest perturbation would cause it to either collapse or expand. Einstein himself initially dismissed Friedmann's results, calling them mathematically suspicious. He would later retract that criticism. Hubble entered this picture without knowing about either Lemaître or Friedmann's theoretical work. He was simply following the data, using the distance measurements he had painstakingly assembled through Cepheid observations, and combining them with Slipher's redshift data plus new redshift measurements of his own. Hubble noticed a pattern. The farther away a galaxy was, the faster it appeared to be moving away from us.
This relationship was not approximate, it was proportional.
Double the distance, and the recession speed doubled. Triple the distance, and the recession speed tripled. This is a pattern that emerges specifically from an expanding universe. Imagine dots scattered across the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. A dot that was farther away from you to begin with moves away faster, not because it has a higher intrinsic speed, but because there is simply more stretching fabric between you and it. This is what Hubble had detected. Not just that galaxies were moving, but that space itself was expanding, carrying galaxies apart like raisins in a rising loaf of bread. Hubble published this finding in 1929. It transformed cosmology. Lemaître's expanding universe theory gained immediate support, and over the following decades, it evolved into what we now call the Big Bang model, the idea that the universe began in an extraordinarily hot, dense state and has been expanding and cooling ever since. The rate at which the universe is expanding, the slope of the relationship between a galaxy's distance and its recession speed, became known as the Hubble Constant. Hubble's original estimate placed this value at roughly 500 kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light-years. So Hubble was saying that for every 3.26 million light-years of distance between 2 points in space, those points are moving apart at roughly 500 kilometers per second. That initial estimate turned out to be significantly too high. Hubble had made certain assumptions about how different types of variable stars behave that were later revised. As better data came in, the value was corrected downward over decades of subsequent work. But the Hubble constant remained central to everything. It sets the age of the universe. Run the expansion backward and you can calculate when everything was compressed into a single point. It sets the size of the observable universe. It feeds into calculations of how dark matter clumps, how galaxies form, how the large-scale structure of the cosmos evolved over billions of years. Getting the Hubble constant right is not an academic exercise. It is a load-bearing pillar of modern physics. Today, Astronomers use two fundamentally different approaches to measure this value. Each one is independent of the other. Each one relies on entirely different physics and different observations. And for decades, scientists assumed that as both methods improved, they would converge on the same number. They have not. That failure of convergence is what cosmologists now call the Hubble Tension. The first method is sometimes called the late universe or distance ladder approach. It works by measuring the expansion as it exists right now using a chain of calibrated distance measurements. The process works in stages. First, you use parallax to measure the distances to the nearest stars with geometric precision. You simply observe how a nearby star appears to shift relative to distant background stars as Earth moves around the Sun, and basic trigonometry gives you the distance. This works for stars within a few thousand light years. At greater distances, you switch to Cepheid variable stars, just as Hubble did. Because you know their intrinsic brightness, you can determine their distance from how bright they appear. Cepheids are visible in galaxies tens of millions of light-years away. At even greater distances, you use type Ia supernovae, stellar explosions that always produce roughly the same peak brightness, because they involve a white dwarf star accumulating matter until it crosses a specific mass threshold. These supernovae are visible across billions of light-years. They serve as the topmost rung of the distance ladder, allowing astronomers to extend their reach across a significant fraction of the observable universe. Using this chain of calibrated measurements, combined with redshift observations of distant galaxies, astronomers have measured the Hubble constant at approximately 73.5 kilometers per second per megaparsec. This number has been confirmed through multiple independent observations and refined over years of careful work. The second method is the early universe approach. Instead of measuring the universe as it exists now, it essentially rewinds the cosmic clock back to just after the Big Bang and calculates what the expansion rate should be given initial conditions. This technique relies on a relic glow of radiation called the cosmic microwave background. In the first few 100,000 years after the Big Bang, the universe was so hot and dense that it was opaque. Photons could not travel freely because they were constantly colliding with charged particles. Then, as the universe expanded and cooled to roughly 3,000 degrees Celsius, electrons combined with protons to form neutral hydrogen atoms for the first time. Suddenly, the universe became transparent and light could travel freely. That moment released a flood of radiation that has been traveling through space ever since. Today, after 13.8 billion years of cosmic expansion, that radiation has cooled to just 2.7 degrees above absolute zero. It fills the entire sky uniformly, the cosmic microwave background. The existence of this radiation was predicted in 1948 by Ralph Alpher and Robert Herman. It was accidentally discovered in 1965 by Arno Penzias and Robert Wilson at Bell Labs, who noticed an unexplained microwave noise in their antenna that persisted no matter which direction they pointed it. They initially suspected the signal was being caused by pigeon droppings on the antenna. When cleaning the antenna made no difference, they realized they had stumbled onto something far more significant. The discovery earned them the Nobel Prize in Physics. For years, the cosmic microwave background was known only as a uniform glow. But in the early 1990s, the COBE satellite detected tiny fluctuations in its temperature, variations of just 1 part in 100,000. These fluctuations were the seeds of all the structure in the universe. The slightly denser regions eventually collapsed under gravity to form the first stars, galaxies, and galaxy clusters. The slightly less dense regions became the vast cosmic voids that separate galaxy filaments today. In 2003, the Wilkinson Microwave Anisotropy Probe released a detailed all-sky map of these fluctuations. Then, in 2013, the European Space Agency's Planck satellite produced an even more precise map, measuring temperature differences across the entire sky at incredible resolution. When cosmologists take the pattern of fluctuations in the cosmic microwave background and mathematically evolve it forward in time, applying the known physics of gravity, dark matter, and dark energy, they get a predicted universe that closely matches the one we actually observe, except for one crucial number. Their predicted Hubble constant comes out to 67.4 kilometers per second per megaparsec. And there is the problem: 73.5 from the distance ladder, 67.4 from the cosmic microwave background, a difference of roughly 9%. 9% might not sound enormous, but in physics, when two independent methods measuring the same physical quantity disagree at this level of statistical confidence, especially when both measurements have been refined to account for potential systematic errors, the discrepancy is not something you can shrug away. The Hubble tension, as this disagreement has come to be known, currently sits at a statistical significance of around 5 sigma. In particle physics, 5 sigma is the threshold required to claim a discovery. In this context, it means there is roughly a 1 in 3.5 million chance that the discrepancy is due to random measurement error alone. Something real is causing it. To understand why two methods measuring the same thing give different answers, consider that the distance ladder measures the universe as it expands right now. The cosmic microwave background method measures the universe as it was almost 14 billion years ago, then extrapolates forward using our best theoretical model. If those two numbers disagree, one of 3 things must be true. Either one or both measurements have a hidden systematic error we have not yet identified, or the model used to evolve the early universe forward in time is missing something important, or our underlying physics is wrong. For years, many astronomers assumed the first explanation was most likely. Measurement errors in astronomy are notoriously difficult to eliminate completely. Each rung of the distance ladder introduces its own potential for systematic bias. Perhaps there was something wrong with how Cepheid variables were being calibrated. Perhaps the cosmic microwave background analysis was missing some subtle effect. But independent measurements have steadily reinforced both sides of the tension. The distance ladder result has been confirmed not just through Cepheids and Type Ia supernovae, but through entirely different methods. In 2020, astronomer D.W. Pesce and colleagues used a phenomenon called megamasers to measure the Hubble constant. Megamasers are regions around supermassive black holes at the centers of galaxies where certain molecules, particularly water vapor, amplify microwave radiation in the same way a laser amplifies visible light, except at microwave frequencies and at colossal energies. The microwave emissions from megamasers can be mapped with extraordinary precision using radio telescope arrays. Because the geometry of these orbiting maser clouds around a black hole is well understood, astronomers can calculate very accurate distances to megamaser hosting galaxies without relying on any of the traditional distance ladder rungs. The result, a Hubble constant of 73.9 kilometers per second per megaparsec, with 95 to 99% confidence, firmly on the high side of the tension. Then in late 2024, a team led by Daniel Skolnick and Adam G. Rees used data from the Dark Energy Spectroscopic Instrument to study 12 Type Ia supernovae scattered across the Coma galaxy cluster, roughly 320 million light-years away. Their result was even higher, a Hubble constant of 76.5 kilometers per second per megaparsec. The Coma cluster is one of the most well-studied galaxy clusters in the sky, making it a particularly clean environment for this kind of measurement. In 2025, researchers from the Inter-University Center for Astronomy and Astrophysics in India took a different approach, using a category of variable stars called Mira variables as distance anchors. Mira variables are red giant stars that pulsate in brightness over very long periods, sometimes several hundred days or more. Like Cepheid variables, the period of their pulsation correlates with their intrinsic luminosity, making them usable as standard candles. When the team calibrated nearby Mira variables in our own galaxy and then used them to measure distances to Mira variables in other galaxies, they arrived at a Hubble constant of 73 kilometers per second per megaparsec. Different method, consistent answer, squarely on the high side of the tension. Meanwhile, the cosmic microwave background side of the argument has also grown stronger. Increasingly precise analysis of the Planck data, cross-checked with other large-scale structure surveys, continues to return values clustered around 67 to 68 kilometers per second per megaparsec. The early universe prediction has not budged toward the higher values. This is the core of the crisis. The two sets of measurements are not converging. If anything, as individual measurements have become more precise and their error bars have shrunk, the gap has become more statistically significant, not less. Skolnick, whose supernovae study returned the value of 76.5, stated publicly that the standard cosmological model might be broken. His phrasing was deliberate and measured. coming from someone who does this work professionally and understands what such a statement implies. The standard cosmological model in question is known as the lambda-cold dark matter model, abbreviated as Lambda-CDM. The lambda refers to a cosmological constant, a term originally introduced by Einstein to represent a form of energy embedded in the fabric of space itself, which we now call dark energy. The cold dark matter component refers to the invisible, gravitationally attractive matter that makes up roughly 27% of the universe's total energy content and forms the scaffolding around which galaxies and galaxy clusters organize. Lambda-CDM emerged as the consensus framework in the late 1990s, when two separate teams studying Type Ia supernovae at high distances discovered something nobody expected. The expansion of the universe is not slowing down. It is speeding up. Dark energy, whatever it is, acts as a repulsive force on cosmic scales, pushing the expansion rate higher and higher as space continues to grow. This discovery earned the Nobel Prize in Physics in 2011. Dark energy makes up roughly 68% of the universe's total energy content. Despite its dominant presence, we do not know what it is at a fundamental level. We describe it mathematically as a constant energy density of empty space, meaning as the universe expands and the volume of space increases, the total amount of dark energy grows proportionally. This ever-increasing reservoir of repulsive energy is why the expansion accelerates over time. Lambda-CDM has been enormously successful. It predicts the distribution of galaxies across the sky, the abundance of galaxy clusters, the observed patterns in the cosmic microwave background, the formation of large-scale cosmic structure, and the general evolution of the universe from a hot early state to the one we inhabit today. But it is a model built on parameters. If those parameters are wrong, if the Hubble constant embedded in the model does not match the actual expansion rate of the real universe, then the model's other predictions become suspect as well. The implications ripple outward. If the true Hubble constant is the lower value predicted by the cosmic microwave background, approximately 67.4 kilometers per second per megaparsec, then the universe is about 13.8 billion years old, as current models suggest, and the expansion will continue at a relatively predictable rate driven by a constant dark energy. This is the calm, orderly cosmic future that Lambda-CDM describes. But if the true Hubble constant is the higher value measured through redshift observations and independent distance measurements, closer to 73 or 76, then something is wrong with the model. The universe would be expanding faster than Lambda-CDM predicts from the initial conditions it specifies. This implies either that the early universe was different from what we think, that dark energy is not constant but has grown stronger over time, that dark matter behaves differently than assumed, or that general relativity itself breaks down at cosmological scales. A universe with a higher true Hubble constant might also be somewhat younger, perhaps 12 to 13 billion years old, though the age depends on exactly what parameters need to change. Each of these possibilities has profound consequences. Dark energy that changes over time, sometimes called dynamic dark energy or quintessence, would require entirely new physics to describe. A modification to general relativity at cosmic scales would shake the bedrock of 20th century physics in a way that has no modern parallel. Physicists and cosmologists have spent decades building precision instruments and conducting exquisitely detailed observations in order to nail down the parameters of Lambda-CDM. The thought that those parameters might be fundamentally wrong is not alarming in the way a natural disaster is alarming. It is alarming in the way a crack in the foundation of a building is alarming. You cannot simply plaster over it. Several theoretical proposals have been put forward to reconcile the tension. One class of ideas involves early dark energy, a form of energy that existed in the universe prior to the release of the cosmic microwave background and caused the universe to expand slightly faster during that early period. This would change the acoustic scale of the fluctuations in the microwave background, effectively adjusting the ruler that the Planck data uses to infer the Hubble constant. The change would push the early universe prediction upward toward the late universe measurements. The problem is that early dark energy models are constrained by other observations. If you adjust them to fix the Hubble tension, they tend to create new tensions elsewhere. For example, in the distribution of matter in the universe, or in the observed clustering of galaxies. Fixing one thing breaks something else. This is a common pattern when theorists try to patch a model that is under stress. Another family of proposals involves decaying dark matter. The idea that some fraction of the dark matter in the universe is unstable and converts into other forms of energy over long time scales. This would change the universe's energy budget as time passes, altering the expansion history in a way that might accommodate both the early and late measurements. But there is currently no direct observational evidence for dark matter decay, and particle physics offers no compelling candidate for this kind of unstable dark matter. Some theorists have explored modifications to the equation of state for dark energy, a parameter, commonly denoted with the letter W, that describes the ratio of dark energy's pressure to its energy density. In standard Lambda-CDM, this parameter is exactly -1. If it departs from -1, dark energy's behavior changes over time. Recent observations from the Dark Energy Spectroscopic Instrument have provided intriguing hints that the dark energy equation of state might be slightly different from -1, suggesting that dark energy could evolve, though the evidence is not yet definitive enough to overturn the standard model. Then, in 2025, a team of researchers proposed an idea that initially sounds unusual, but turns out to be mathematically elegant. The universe might be rotating. The paper, authored by Balázs Endre-Szigeti, István Sápudi, Imre Barna, and Gergely Gábor Barna-Földi, suggests that the cosmos as a whole might be executing an extremely slow spin, so slow that it completes one rotation every 500 billion years. For context, the current age of the universe is about 13.8 billion years, meaning this hypothetical rotation is so gradual that the universe has barely moved through a tiny fraction of one full revolution since the Big Bang. At such an imperceptibly slow rate, there would be no detectable effect in any single direction we observe. The rotation would be far too subtle to show up in the anisotropy of the cosmic microwave background, or in the large-scale distribution of galaxies, or in any other dataset we currently have. It would be, by design, hidden beneath our current detection thresholds. But its effects on the expansion history would not be invisible. The authors showed that when a rotation term is introduced into the cosmological equations, it modifies how the expansion rate evolves over time. Their preliminary calculations suggest that a slowly rotating universe would naturally produce a lower expansion rate in its early history, consistent with what the cosmic microwave background measurements imply, and then a higher expansion rate at later times, consistent with what the distance ladder and redshift measurements observe. In other words, the two values of the Hubble constant that currently contradict each other might not actually be measuring different things. They might be measuring the same physical quantity at two different points in the universe's history, and the discrepancy arises because dark energy is not constant after all, or rather, because rotation is effectively playing the same role. One reason this idea has attracted attention is that it does not require new physics. It does not invoke exotic particles, new fundamental forces, or modifications to general relativity. Rotating spacetimes are perfectly permissible within general relativity. The mathematics that describes a rotating universe has been studied for decades. The most well-known example is the Gödel metric, developed by the logician and mathematician Kurt Gödel in 1949. Gödel showed that Einstein's equations permit a solution where the entire universe rotates, and he famously used this to argue that time travel might be theoretically possible in such a universe. Gödel's rotating universe was not considered a realistic description of our cosmos, but it established that rotation is not forbidden by the laws of physics. The authors are careful to describe their 2025 result as preliminary. They focused specifically on reproducing the Hubble constant discrepancy and did not attempt to check their rotating model against the full suite of cosmological observations. Doing so would require much more complex numerical simulations, the kind that take months or years to construct and validate. The next stage of testing would involve asking whether a slowly rotating universe also correctly predicts the observed pattern of temperature fluctuations in the cosmic microwave background, the matter power spectrum measured by galaxy surveys, the abundance of light elements produced in the first few minutes after the Big Bang, and other precision cosmological benchmarks. If the rotating universe model survives these tests, It would represent a significant conceptual shift, not a revolution in fundamental physics, since it stays within general relativity, but a change in our picture of the cosmos that would require revising nearly every cosmological parameter we have measured. The age, composition, and future of the universe are all derived from a model that assumes no global rotation. Introducing rotation into that model would cascade through all those calculations. There is also a deeper philosophical point worth making. Rotation is ubiquitous in the universe at every scale we can observe. Planets spin on their axes. Moons orbit planets. Planets orbit stars. Stars orbit the centers of galaxies. Galaxies rotate. Galaxy clusters contain rotating structures. Even the filaments and sheets of the cosmic web show signs of angular momentum. At every level of structure, from the smallest asteroids to the largest superclusters, rotation appears to be a natural consequence of how matter organizes itself under gravity. It would not be conceptually strange if the universe as a whole also had some angular momentum left over. From its initial conditions, the absence of measurable global rotation in the current data is not evidence that rotation does not exist. It is merely a constraint on how fast any rotation could be. The model being proposed sits well within that constraint. That is part of what makes it scientifically testable rather than speculative. It makes a specific, quantitative prediction that can in principle be confirmed or ruled out by better observations. What those better observations would look like is an active area of discussion. One approach involves searching for a subtle directional asymmetry in the cosmic microwave background, a departure from perfect isotropy that might be imprinted by a rotating universe. Existing CMB data has been analyzed for such patterns with no clear detection, but a rotating universe model with a period of 500 billion years would produce effects near or below the current detection threshold. Future CMB experiments with higher sensitivity might be able to reach those levels. Another avenue involves using the full three-dimensional map of the universe that large galaxy surveys are assembling. The Dark Energy Spectroscopic Instrument is currently mapping tens of millions of galaxies across a significant fraction of the observable universe, measuring their distances and redshifts with extraordinary precision. If the universe is rotating, that rotation would imprint a distinctive signature in the statistical distribution of galaxies across the sky, a subtle preferred direction that a static universe would not produce. Detecting this would require careful analysis, since many other effects can mimic a preferred direction, but it is within the realm of what current and near future surveys might be able to probe. The fact that the Hubble tension remains unresolved after more than a decade of intensive work tells us something important about where we are in the history of physics. The 20th century produced two revolutionary frameworks, general relativity and quantum mechanics, that describe the universe with extraordinary precision in their respective domains. Yet those two frameworks are fundamentally incompatible with each other. Physicists have been trying to reconcile them into a single unified theory for nearly a century, with only partial success. Most cosmological puzzles, the nature of dark matter, the source of dark energy, the conditions of the very early universe, live at the boundary between these two frameworks. The Hubble tension is no exception. It is a clue, waiting to be interpreted correctly. Whether it points to something mundane, a systematic error in our distance measurements that no one has yet identified, or something genuinely radical, a modification to our understanding of dark energy, dark matter, or even the global structure of space-time, we cannot yet say. What we can say is that the evidence against a simple measurement error grows stronger with each new independent measurement. The megamaser result, the supernovae in the Coma cluster, the Mira variable analysis, all of these use completely different physical phenomena to measure the same quantity, and all of them agree with the high value. The probability that all of these independent measurements are systematically biased in the same direction by the same amount continues to shrink. As more data accumulates, we should also appreciate how unusual it is for the universe to offer us two windows into its past and present that can each be used to measure its expansion rate. The fact that we have both the cosmic microwave background, a snapshot of the universe from 380,000 years after the Big Bang, and the large-scale redshift of galaxies across billions of light-years of our current universe is itself remarkable. Most questions in cosmology have only one observational handle. The Hubble constant is special because it can be approached from both directions which is exactly why the disagreement is so informative. Consider what each value implies independently. The early universe measurement, around 67 kilometers per second per megaparsec, combined with the measured density of matter and dark energy, gives a universe that is 13.8 billion years old. This value is consistent with the ages of the oldest stars we can measure, ancient red giants in globular clusters, whose ages are estimated through stellar evolution models to be around 13 to 13.5 billion years. If the universe were younger, some of those stars would be older than the universe itself, which is obviously impossible. This places a natural sanity check on how high the Hubble constant can actually be. The late universe measurements, around 73 to 76 kilometers per second per megaparsec, if taken at face value and combined with the same matter and dark energy densities from Planck, produce a universe somewhat younger, around 12 to 12.5 billion years old. This does not immediately violate the stellar age constraint, but it pushes in that direction, adjusting the matter and dark energy densities to accommodate a higher Hubble constant while keeping the age reasonable requires a different cosmological recipe, one that would also affect predictions for galaxy formation, the cosmic microwave background spectrum, and other observables. This is why theorists emphasize that the Hubble tension is not an isolated problem. Changing any one part of Lambda-CDM affects many other parts simultaneously. A solution that fixes the tension while breaking everything else is not a solution. A true resolution must reproduce all of what Lambda-CDM currently gets right, while also explaining the discrepancy in the expansion rate. That is an extremely demanding constraint. It is also, from a scientific perspective, extremely valuable, because it narrows the space of possible explanations. Any new theory of dark energy, dark matter, or cosmic evolution will be forced to thread this very specific needle. The Hubble tension is functioning as a precision filter for new ideas in cosmology. Looking ahead, the next decade will bring powerful new tools to bear on this question. The Euclid Space Telescope, launched by the European Space Agency, is conducting a wide-field survey of galaxy shapes and positions that will provide unprecedented constraints on dark energy and the growth of cosmic structure. The Nancy Grace Roman Space Telescope, formerly known as the Wide Field Infrared Survey Telescope, will search for supernovae at enormous distances and measure Cepheid distances with exceptional precision using its large infrared detector. The Vera Rubin Observatory in Chile will image the entire southern sky every few nights for 10 years, building a data set of billions of galaxies and detecting hundreds of thousands of supernovae. These instruments are not being built specifically to resolve the Hubble tension. They have broad scientific goals across cosmology, exoplanet science, and galactic astronomy, but the data they produce will inevitably either sharpen the tension into an undeniable crisis or provide new evidence that helps resolve it. Each measurement that arrives with smaller error bars than its predecessors either confirms the gap or closes it. So far, the gap has not closed. There is another dimension to this story that deserves attention. The Hubble tension is unusual in that it is a quantitative disagreement that has persisted through multiple generations of technological improvement. In the 1980s and early 90s, the Hubble constant debate was much messier. Different teams using the same distance ladder techniques were getting values ranging from 50 to 100 kilometers per second per megaparsec, a factor of two difference that reflected genuine uncertainty in the underlying data. The Hubble Space Telescope was partly designed to resolve this debate by providing sharp enough images to identify Cepheid variables in galaxies much farther than ground-based telescopes could reach. By the early 2000s, the key project on the Hubble Space Telescope had narrowed the uncertainty considerably, settling on a value around 72 plus or minus 8 kilometers per second per megaparsec. Simultaneously, the first precise measurements of the cosmic microwave background from WMAP gave a value around 71. There was no tension then. Within the error bars, the two methods agreed. As both measurements became more precise over the following 2 decades, the error bars shrank. Normally, when measurements improve, previously consistent results stay consistent. Instead, the central values drifted apart. The late universe value went up slightly, settling around 73. The early universe value came down, settling around 67. And as the error bars shrank, the overlap between the two measurements disappeared entirely. That is the precise moment when a discrepancy becomes a tension, not when the numbers differ, but when the uncertainties shrink to the point where the numbers cannot simultaneously be correct. That sequence of events, improving precision, revealing a problem rather than resolving one, is one of the most productive things that can happen in physics. It happened with Mercury's orbit in the 19th century. Newtonian gravity could not quite account for the precession of Mercury's orbit, and that tiny discrepancy eventually pointed toward general relativity. It happened with the decay rates of certain subatomic particles, where a missing fraction of energy seemed to violate conservation laws and eventually led to the discovery of the neutrino. Small, precise discrepancies are often where new physics hides. The Hubble tension may be the latest entry in that lineage, or it may turn out to have a more prosaic explanation, some overlooked systematic effect in one of the measurement pipelines that a future calibration will correct. But the fact that it has persisted through multiple independent confirmation attempts, using different instruments, different calibrators, and different physical phenomena, suggests that the simple explanation is becoming less and less likely. What we know for certain is that two of the most powerful techniques in observational cosmology are giving different answers about the most fundamental characteristic of our universe's evolution. What we do not know is why. That uncertainty lives at the very edge of current knowledge, in the gap between theory and observation where physics tends to make its most surprising discoveries. The rotating universe hypothesis from the 2025 paper may ultimately not survive contact with a full set of cosmological observations. Many elegant ideas do not, but it illustrates how the Hubble tension is now stimulating genuinely creative theoretical thinking. Not just incremental refinements to Lambda-CDM, but deeper questions about assumptions we have embedded in our models from the very beginning. The assumption that the universe has no global rotation has never been directly tested at the level of precision this model would require. Testing it properly will require the next generation of cosmological surveys, the same spirit of inquiry that led Hubble to identify a Cepheid variable in Andromeda and measure the size of the universe for the first time is driving today's astronomers to interrogate their most basic assumptions. The numbers that describe our cosmos are not sacred. They are measurements, and measurements can always be improved. What cannot be taken for granted is the model that interprets those measurements. The Hubble tension is asking us to look at that model with fresh eyes and to consider whether the universe we thought we understood is telling us something new. If you have found this exploration of one of modern science's most active frontiers compelling, consider sharing it with someone who appreciates the deep questions about the cosmos. The conversation around the Hubble tension is ongoing, and the next major development could come from any direction: a new telescope, a new theoretical framework, or simply a more careful look at data we already have. That is what makes science worth following. Astronomers are not standing still. Every year, new surveys add millions of galaxies to our redshift catalogs. Every year, the precision of microwave background measurements improves. Every year, new distance calibrators, Mira variables, megamasers, gravitational wave standard sirens from merging neutron stars are brought to bear on the same fundamental question. The answer, when it arrives, will not just tell us the correct value of a single number. It will tell us something deep about the structure of the universe, whether the laws of physics we have built our understanding on are complete, or whether there is another layer of reality waiting to be uncovered. That prospect is not unsettling. It is exactly what science is for. The story of the Hubble constant is, in a deeper sense, the story of how science works at its most advanced frontier. It is not a story of confident proclamations and settled truths. It is a story of measurement, disagreement, refinement, and the very human process of trying to understand something that no person has ever directly seen or touched. The large-scale structure of space-time itself. Edwin Hubble did not set out in 1929 to prove the universe was expanding. He set out to measure the distances to certain fuzzy patches of light. The discovery of cosmic expansion was the interpretation that followed from the data. That is a subtle but important point. The universe does not announce its properties. Scientists extract them imperfectly and iteratively by building instruments sensitive enough to detect signals from the edge of the observable cosmos, developing mathematical frameworks to interpret those signals, and then checking whether the resulting picture is self-consistent. The Hubble constant is currently failing that self-consistency check. Two measurements, each conducted with extraordinary care and refined over decades, describe two different universes. The cosmological model says there is only one universe and it should have a single expansion rate. Something has to give. There is a version of this story in which the resolution turns out to be straightforward, a previously unidentified systematic bias in the way Cepheid distances are calibrated. For example, Cepheid variables are not perfectly uniform objects. They come in different chemical compositions, exist in different environments, and their period-luminosity relationship has been calibrated primarily in relatively metal-poor stars in the Large Magellanic Cloud, a satellite galaxy of our Milky Way. If the Cepheid calibration in more chemically complex galaxies, like the ones in the Coma cluster, is subtly different from what we assume, the resulting distance estimates could be systematically off. This hypothesis has been explored, and some evidence for a compositional effect exists, but it is not large enough to fully close the gap. The tension persists even when astronomers try to account for it. There is another version of this story in which the resolution requires genuine new physics, not a tweak to a calibration, but a revision to the fundamental picture. Perhaps dark energy is not a cosmological constant after all. Perhaps its density changes as the universe expands, growing stronger or weaker in ways that current models do not account for. A dark energy that was slightly more subdued in the early universe and has since grown stronger would produce exactly the pattern we observe: a lower expansion rate inferred from early universe data and a higher expansion rate measured from the current universe. The Dark Energy Spectroscopic Instrument's latest results, released in 2025, hint at precisely this kind of evolving dark energy, though the statistical significance is not yet high, enough to claim a definitive detection, gravitational. Wave observatories offer yet another independent path toward resolving the tension. When two neutron stars spiral together and merge, they produce both gravitational waves, ripples in spacetime that propagate at the speed of light, and a flash of electromagnetic radiation. By measuring the strength of the gravitational wave signal, astronomers can calculate the distance to the merger event purely from the physics of gravity, without relying on any rungs of the distance ladder. The redshift of the merger's host galaxy then gives the recession velocity. Combining these two pieces of information directly yields the Hubble constant. This technique was first demonstrated in 2017 with the merger event known as GW17000817, which gave a Hubble constant of approximately 70 kilometers per second per megaparsec, with large uncertainties because it was just one event. As the gravitational wave detector network detects more binary neutron star mergers in coming years, this independent measurement will become more precise, and its position relative to the Hubble tension will become much more informative. The Laser Interferometer Gravitational Wave Observatory, along with its European counterpart Virgo and the Japanese detector Kagra, is currently in its fourth observing run. Each run brings improved sensitivity and a larger detection volume, with dozens or eventually hundreds of binary neutron star mergers providing independent distance measurements. This method will eventually become competitive with the distance ladder and cosmic microwave background approaches. If the gravitational wave method agrees with the high value from the distance ladder, the case for new physics will become overwhelming. If it agrees with the low value from the early universe approach, attention will shift intensely toward finding the systematic error in the distance ladder. Meanwhile, there is a different class of cosmological observations that has begun to create its own tensions, separate from but related to the Hubble constant problem. The sigma-8 tension, named after a parameter that describes the amplitude of matter clustering in the universe, shows a similar pattern. The cosmic microwave background predicts that matter should be somewhat more tightly clustered than what we observe in galaxy surveys. Again, the early universe and late universe measurements disagree. And again, the disagreement cannot easily be explained by measurement errors alone. Some theorists believe the Hubble tension and the sigma-8 tension share a common cause, that some single modification to the cosmological model would resolve both simultaneously. If that is the case, it narrows the space of viable solutions considerably, since any proposed fix must address both discrepancies at once. Early dark energy models, for example, have been shown to improve the Hubble tension but worsen the sigma-8 tension, which is part of why they have not been accepted as the definitive answer, a model that truly resolves the Hubble tension without introducing new tensions elsewhere would need to be extraordinarily precise in its adjustments. the universe's expansion history, the growth of structure, the pattern of the cosmic microwave background fluctuations, and the abundance of light elements from the first few minutes after the Big Bang are all interconnected through the same set of cosmological equations. Any modification touches all of these observables simultaneously. This interconnection is what makes the problem hard, and also what makes it rich. There are many independent datasets to use as constraints, which means that any proposed solution faces a dense gauntlet of tests. The abundances of light elements from Big Bang nucleosynthesis are particularly important in this context. In the first few minutes after the Big Bang, when the universe was a hot plasma of protons, neutrons, and electrons, nuclear reactions fused some of those particles into helium-4, helium-3, deuterium, and tiny amounts of lithium. The precise ratios of these light elements that emerged from that early hot phase depend on the density of ordinary baryonic matter and the expansion rate during nucleosynthesis. The predicted abundances from standard nucleosynthesis theory match the observed primordial abundances extremely well. It is one of the great quantitative successes of cosmology. Any modification to the early universe expansion rate risks disrupting this agreement, since a different expansion rate during the first few minutes would change the neutron-to-proton ratio and alter the final element abundances. This places tight constraints on any model that tries to modify the early universe expansion history to resolve the Hubble tension. The rotating universe idea is attractive partly because it addresses the expansion history without necessarily altering the very early universe conditions that nucleosynthesis depends on. The rotation proposed in the 2025 paper would have its primary effect on the expansion dynamics over cosmological timescales, not during the first 3 minutes. Whether this holds up under detailed scrutiny, whether a rotating cosmological model can simultaneously reproduce nucleosynthesis abundances, cosmic microwave background fluctuations, large-scale structure, and both values of the Hubble constant remains to be seen. The authors themselves emphasize that this is the necessary next step. What would it mean philosophically and scientifically if the universe turned out to have a global rotation? It would mean that the cosmos has a preferred axis, a direction in space that is, in some sense, special. This would be a subtle violation of one of the foundational assumptions of modern cosmology, that the universe looks the same from every position and in every direction. What physicists call the cosmological principle. Observations support this principle impressively well on the largest scales. The cosmic microwave background is isotropic to better than 1 part in 100,000, and the distribution of galaxies across the sky becomes increasingly uniform as you look at larger and larger scales. A very slow rotation would not necessarily violate the cosmological principle in any detectable way at current sensitivities. The universe could appear homogeneous and isotropic to all our instruments while still having an extremely subtle global angular momentum. But philosophically, it would mean that there is a preferred direction, the rotation axis, embedded in the structure of the universe. That is a conceptually significant shift from a universe that is truly symmetric in all directions. It would raise immediate questions about the origin of that angular momentum. Where did it come from? What process in the earliest moments of the universe's history would have imparted a net spin to the cosmos? One possibility involves the initial conditions at the Big Bang itself. In inflationary cosmology, the leading model for the very early universe, a period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang, stretched quantum fluctuations to cosmological scales and set up the initial conditions for everything that followed. Inflation is typically modeled as producing a universe with no preferred direction, but inflation models are parameterized by a specific field, the inflaton, and different choices of inflaton potential produce different observational signatures. Some variants of inflation could, in principle, introduce a small net angular momentum. Whether any of these variants make predictions that match other cosmological observations while also producing the small rotation required to resolve the Hubble tension is an open question. Another possibility is that the rotation does not originate from the Big Bang itself, but from some subsequent process, perhaps a phase transition in the early universe, or the formation of the large-scale cosmic web, which is itself far from isotropic at intermediate scales. The filaments and voids that make up the large-scale structure of the universe have complex geometries and angular momentum distributions. Whether the aggregation of all this local angular momentum could add up to a coherent global rotation is a question for numerical simulations. These are deep questions, and they will not be answered quickly. Cosmology advances in long cycles, driven by the construction of new observatories, the collection of new data over years or decades, and the painstaking analysis that follows. The resolution of the Hubble tension, when it comes, will likely emerge not from a single dramatic announcement but from a gradual accumulation of evidence, one independent measurement at a time, until the weight of the data decisively favors one explanation over the others. That is how science, at this level, works. It is patient, iterative, and often frustrating. It requires enormous international collaborations, telescopes on mountaintops and in orbit, supercomputers running simulations that would take a human lifetime to complete by hand, and the intellectual courage to report results that contradict the established model when the data demands it. The physicists and astronomers working on the Hubble tension are doing all of these things simultaneously. The Hubble constant was the number that opened the cosmos. When Hubble first published his distance-velocity relationship in 1929, it was the number that proved the universe was larger than anyone had imagined, that it was dynamic rather than static, and that it had a history stretching back to a definable beginning. Nearly a century later, that same number is now telling us that our understanding of the cosmos, vast and sophisticated as it has become, is still incomplete. There is something we are missing, something fundamental about the universe that does not yet fit neatly into our equations. That incompleteness is not a failure of science, it is its most honest expression. Every answer in physics reveals deeper questions underneath it. The fact that we can measure the expansion rate of the universe to percent-level precision, from observations of objects billions of light-years away, and then discover that two independent methods give answers that disagree at a statistically decisive level, is itself a remarkable achievement. It means our measurements have become precise enough to detect a crack in the foundation, which is the first step toward building a stronger one. The universe has been expanding for billions of years, indifferent to our attempts to measure it, but we keep building better instruments, developing more sophisticated theoretical frameworks, and asking sharper questions. The Hubble tension is the universe pushing back, telling us, as it always has, that there is more to learn. There is an underappreciated human dimension to this story. Science is often presented as a purely logical enterprise. Data goes in, conclusions come out, and the truth is whatever the numbers say. But the Hubble tension reveals something more complicated about how knowledge actually advances. The two camps in this debate are not enemies. They are colleagues who use different telescopes, analyze different data sets, and sometimes interpret the same uncertainties in different ways. The tension between them is not a personal conflict. It is a productive scientific disagreement, the kind that has historically been resolved only by accumulating evidence so overwhelming that it leaves no room for alternative interpretations. In that sense, the Hubble tension resembles the debate over the nature of the nebulae in the early 20th century. For years, astronomers argued about whether objects like Andromeda were clouds of gas within the Milky Way or independent galaxies in their own right. The debate was not resolved by clever argumentation. It was resolved when Hubble found a Cepheid variable in Andromeda and measured a distance that put the question to rest. The equivalent moment for the Hubble tension has not yet arrived, but the instruments being built today are capable of delivering it. The James Webb Space Telescope, launched in December 2021 and operating since 2022, has already contributed to this debate. Its infrared sensitivity and extraordinary resolution allow it to identify Cepheid variables in galaxies much farther away than the Hubble Space Telescope could reach, and with less contamination from crowded stellar fields. Early results from the James Webb Space Telescope were eagerly awaited by both camps. What the telescope found was that the high value of the Hubble constant from the distance ladder held up. The concern that crowding effects in the Hubble Space Telescope images were systematically biasing Cepheid measurements was not confirmed as a significant source of error. This was an important result. It ruled out one of the most commonly cited potential systematic errors in the distance ladder approach. The Webb telescope is still in the relatively early stages of its scientific mission. Over the coming years, it will measure Cepheid distances to a larger sample of galaxies hosting Type Ia supernovae, extending the distance ladder to greater distances and improving the statistics. Every additional measurement either confirms the tension or narrows it, and the scientific community is watching closely. It is also worth pausing to appreciate the physics that makes all of this measurement possible. The light reaching our telescopes from galaxies hundreds of millions or billions of light-years away left those galaxies long before the solar system formed. The photons that Hubble Space Telescope and James Webb Space Telescope detectors capture were emitted by stars that lived and died before Earth existed. By analyzing the spectrum of that ancient light, the precise pattern of wavelengths it contains, we can determine the recession velocity of its source with extraordinary precision. By comparing that apparent brightness to the known intrinsic brightness of the stars or explosions that emitted it, we can determine the distance. The combination of these two measurements, repeated across thousands of galaxies, gives us the Hubble Constant. The cosmic microwave background method is perhaps even more remarkable. The photons that make up the microwave background were emitted when the universe was 380,000 years old, a time before any stars, any galaxies, any planets existed. Those photons have been traveling through expanding space ever since, redshifting from energetic visible light into faint microwaves. The pattern imprinted on them at the moment of their emission reflects the density fluctuations of the infant universe, shaped by the interplay of radiation pressure and gravity in the hot plasma that filled all of space. By studying that pattern with high precision, we can infer the composition of the universe, the geometry of space, and the initial conditions that set up everything that followed. It is, in a very real sense, a photograph of the universe in its infancy, and we are trying to use it to calculate what the adult universe should look like today. The fact that these two radically different methods, one, measuring light from individual stars and stellar explosions in the modern universe, the other measuring the collective glow of a universe without any stars at all, give answers that disagree is both puzzling and exciting. It is puzzling because our model says they should agree. It is exciting because the disagreement is pointing somewhere new. Many of the most transformative moments in the history of physics have come from small, precise discrepancies. The anomalous precession of Mercury's orbit, an effect of 43 arcseconds per century, almost too small to measure, was a key clue that pointed toward general relativity. The slight discrepancy between the measured magnetic moment of the electron and the prediction from quantum electrodynamics spurred the development of precision quantum field theory. The discovery that the universe's expansion was accelerating, rather than decelerating as expected, came from observing that distant Type Ia supernovae were slightly dimmer than they should have been in a matter-dominated universe, a subtle effect that required years of careful analysis to confirm. The Hubble tension is a discrepancy of roughly 9%. That is far larger than the other historical examples, which makes it both more obvious and, in some ways, more alarming. A 9% error in a fundamental cosmological parameter is not a small systematic bias. It is a significant departure from what the standard model predicts. The fact that it has persisted through a decade of increasingly precise measurements suggests it is real. The question is only what it means. As we look ahead, the convergence of multiple next-generation surveys will make the next decade one of the most scientifically productive in the history of cosmology. The Euclid Satellite, the Nancy Grace Roman Space Telescope, the Vera Rubin Observatory, the Square Kilometre Array Radio Telescope, the Simons Observatory and CMB-S4 for next-generation microwave background measurements, and in the continued operation of LIGO, Virgo, and KEGRA for gravitational wave standard sirens. All of these will contribute fresh, independent constraints on the Hubble constant and the broader cosmological picture. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the world's largest radio telescope by a wide margin. Among its scientific goals is mapping hydrogen gas across enormous volumes of the universe, producing a three-dimensional map of galaxy positions that will rival or exceed what optical surveys can achieve. Radio observations are not subject to the same dust extinction effects that complicate optical surveys, making the Square Kilometre Arrays measurements an important independent check on results from optically based surveys, CMB-S4. The next generation of ground-based cosmic microwave background experiments will measure the microwave background with a sensitivity roughly an order of magnitude better than the Planck satellite achieved. This will allow detection of much more subtle features in the temperature and polarization patterns of the microwave background, potentially revealing new physics that current instruments cannot see. If the early universe expansion rate contains a contribution from some form of new energy or a modification to gravity, CMBS-4 has a realistic chance of detecting its signature. The cumulative picture that emerges from all of these instruments over the next decade will be unprecedented in its precision and scope. Whether it resolves the Hubble tension or deepens it into an undeniable crisis, the result will be transformative. Physics does not often offer controlled experiments with outcomes this consequential. We cannot build a laboratory version of the universe and test our theories directly. We can only observe, measure, and refine. The instruments being built now are the most sophisticated tools humanity has ever created for that purpose. One of the more subtle aspects of the Hubble tension is that it forces cosmologists to examine the philosophical foundations of their work. Cosmology as a science rests on a principle of uniformity, the idea that the same laws of physics operate everywhere and at all times, and that the universe is statistically the same when viewed from any location. This principle cannot be proven. It can only be assumed and then tested by looking for evidence of violations. For decades, it has been tested and found to hold impressively well. The cosmic microwave background is isotropic. The large-scale distribution of galaxies is homogeneous. The laws of atomic physics inferred from spectroscopic observations of distant galaxies match those measured in terrestrial laboratories. But the Hubble tension hints that something about the universe is not uniform in the way we assumed. Either the expansion rate has changed over time in a way our model does not predict, or there is a preferred direction encoded in the fabric of space, or some property of the cosmos varies in a way we have not yet detected. Each of these possibilities would represent a departure from the cleanest version of the cosmological principle, not necessarily a refutation of it, but a qualification of it. Science is full of such qualifications. Newton's laws of motion were not wrong, they were incomplete. They described the motion of objects at everyday velocities with extraordinary accuracy, and they continue to be used every day in engineering and practical applications. But when velocities approach the speed of light, or when gravitational fields become extremely strong, general relativity provides corrections that Newton's laws cannot. Similarly, quantum mechanics does not replace classical physics. It contains it as a limiting case, applicable when quantum effects are small. The progression of science is not usually a sequence of complete revolutions, but of expansions and refinements, where new frameworks subsume the old ones and extend their domain of applicability. Lambda-CDM will likely follow this pattern. Whatever modification is eventually found to resolve the Hubble tension will almost certainly preserve the model's many successes, while extending it to handle the discrepancy. The framework of an expanding universe dominated by dark energy and dark matter, shaped by the initial conditions set at the Big Bang, is supported by too much observational evidence to be simply wrong. It is more likely incomplete, missing some ingredient, some effect, some subtlety that the next generation of measurements will reveal. That ingredient, once found, will not merely resolve a number discrepancy. It will tell us something new about the universe, about the nature of dark energy, or the global geometry of spacetime, or the physics of the very early universe. It will be a discovery in the truest sense, not the correction of an error, but the extension of knowledge into territory that was previously inaccessible. The universe expanded for billions of years before any being existed to observe it. It will continue expanding long after any conceivable civilization has ended. Within that vast sweep of cosmic time, the current moment, when our instruments are just sensitive enough to detect a crack in our best theory of the universe, is an extraordinary one. The Hubble tension may be the first sign of a deeper truth about the cosmos. It is a problem worth caring about, a puzzle worth pursuing, and a reminder that the universe is under no obligation to be simple. What Edwin Hubble began with a Cepheid variable in 1923 continues today in the photon counts of space telescopes, in the microwave maps of the early universe, in the gravitational wave signals from merging neutron stars, and in the minds of thousands of scientists around the world who have dedicated their careers to measuring and understanding the expansion of space. The work is not finished. It may never be truly finished. Science rarely reaches a final endpoint, but each step forward reveals more of what there is to know. And that revelation, however incomplete, is its own reward. To put the scale of the problem in perspective, consider what it means to measure the distance to a galaxy 100 million light-years away. 1 light-year is the distance light travels in 1 year, moving at 300,000 kilometers per second. Over 1 year, that covers roughly 9.5 trillion kilometers. 100 million light-years is therefore approximately 950 quadrillion kilometers. Measuring that distance to an accuracy of a few percent, using the brightness of individual pulsating stars or the peak luminosity of a stellar explosion, is an achievement of staggering precision. The fact that we can do it at all is a testament to a century of accumulated physics, mathematics, and engineering. The cosmic microwave background measurements are equally demanding in a different way. The temperature variations across the microwave sky that encode the initial conditions of the universe are about 100 microkelvin in amplitude, tiny. Fluctuations on top of a background temperature of 2.73 degrees above absolute zero. Detecting these fluctuations requires detectors cooled to within a fraction of a degree of absolute zero, operating in space far from the heat and radio interference of Earth. The Planck satellite achieved this by cooling its detectors to just 1/100th of a degree above absolute zero, colder than any naturally occurring location in the universe, including the space between galaxies. The mathematical analysis that transforms the raw microwave maps from these satellites into precise cosmological parameters involves solving systems of equations with dozens of free parameters, running numerical simulations of cosmic structure formation, and applying statistical techniques that account for the geometry of the sphere, the correlations between different angular scales, and the potential contamination from foreground sources like the Milky Way's own microwave emission. It is science at the limit of what current technology and mathematical methods allow. Given all of this, a 9% discrepancy in the Hubble constant is not a small thing. It is not the kind of error that gets swept away by a better calibration. It has survived the commissioning of the James Webb Space Telescope, the analysis of new supernovae samples, the introduction of entirely new distance indicators like megamasers and Mira variables, and the publication of updated cosmic microwave background analyses from the Planck team. Each time a new measurement is announced, the scientific community watches to see which side of the tension it falls on. So far, measurements based on the current universe cluster consistently around the high value, and measurements based on the early universe cluster consistently around the low value. There is one more proposed explanation worth discussing in detail: the possibility that there is no Hubble tension at all, because the measurements themselves are biased in ways we have not identified. This is a legitimate scientific hypothesis, not mere wishful thinking. Astrophysical measurements are notoriously difficult to make without systematic biases, and the history of the Hubble constant is full of examples where early measurements were wrong because of an unidentified systematic effect. In the 1950s and 60s, astronomers realized that Hubble's original calibration of Cepheid variables was confused by a separate population of stars that had similar periods but different intrinsic luminosities. Correcting for this brought the Hubble constant down by a factor of roughly 2. Later, a confusion between different types of bright stellar objects led to further revisions. Could something similar be happening today? It is possible, but the systematic effect would need to affect all of the independent late universe measurements in the same direction by the same amount. The Cepheid distance ladder, the megamaser measurements, the supernovae in the Coma cluster, the Mira variable measurements. These techniques are not just variations of one another. They rest on completely independent calibrations and physical processes. For all of them to be biased in the same direction by a similar amount would require a remarkable coincidence. The alternative, that the measurements are correct and the model needs updating, is increasingly favored by the community. The question is not really whether there is a Hubble tension. There clearly is. The question is what causes it and what the fix reveals about the true nature of the universe. One underexplored possibility is related to the environment in which the solar system and Milky Way are embedded. We live in a region of space that is part of a large-scale structure called the Laniakea supercluster, which itself sits near the edge of a vast underdensity called the local void. If our local cosmic neighborhood has a slightly different density or expansion history than the universe as a whole, our measurements of the Hubble constant using nearby calibrators could be affected. This idea, sometimes called the local void hypothesis, suggests that the Milky Way sits in a bubble of space that is slightly underdense compared to the cosmic average, because underdense regions expand faster than average. Matter falls away from voids rather than clumping toward overdensities. We might be measuring a locally inflated expansion rate that does not reflect the global average. Studies of the galaxy distribution around the Milky Way do suggest that we are in a somewhat underdense region, but estimates of how much this local environment could bias the Hubble constant have generally concluded that the effect is small, perhaps 1 or 2 kilometers per second per megaparsec, which is not enough to bridge the entire gap of approximately 6 kilometers per second per megaparsec between the two values. So while the local environment probably contributes some systematic effect, it is unlikely to be the primary explanation. The gravitational wave standard siren method offers a particularly clean test of the systematic bias hypothesis. When LIGO detects a binary neutron star merger, the distance measurement comes purely from the amplitude of the gravitational wave signal, which is calculated from fundamental physics, general relativity, and the masses of the merging objects. There is no distance ladder, no stellar calibrator, and no astrophysical assumption about the intrinsic brightness of any object. The distance is obtained directly from the physics of the merger. If the resulting Hubble constant from this method agrees with the high value from the distance ladder, it will be strong evidence that the distance ladder is not systematically biased, because a measurement that shares none of the distance ladder's assumptions reaches the same answer. The first gravitational wave standard siren measurement from the binary neutron star merger GW170817, detected in August 2017, gave a Hubble constant of approximately 70 kilometers per second per megaparsec. With large uncertainties spanning from 62 to 82, the central value sits between the two competing measurements, making it compatible with both within the error bars. This is not helpful for resolving the tension, but it is a proof of concept. The method works, and future detections with smaller uncertainties will narrow the range. LIGO, Virgo, and KGRA are expected to detect dozens of binary neutron star mergers over the next several years as the detectors undergo sensitivity upgrades. By the early 2030s, the cumulative dataset from gravitational wave standard sirens may provide a Hubble constant measurement with uncertainties of just a few percent, precise enough to either confirm one side of the tension or occupy a middle ground that would suggest both sides are affected by systematic errors. This timeline makes the next decade unusually consequential for the future of cosmology. It is also worth noting that the Hubble tension is not the only anomaly in modern cosmology. There are several other observations that sit in tension with the predictions of Lambda-CDM. The sigma-8 tension, already mentioned, describes an apparent discrepancy between the predicted and observed amplitude of matter clustering. The so-called S8 tension is related. It combines the matter density parameter with the sigma-8 parameter in a combination that galaxy-weak lensing surveys measure particularly well. The Hubble tension and S8 tension together suggest that something in our cosmological model is consistently off in the direction of predicting a more clumped, more slowly expanding universe than what we actually observe. A unified explanation for all of these tensions, one modification to the cosmological model that simultaneously resolves the Hubble tension, the S8 tension, and the sigma-8 tension without creating new inconsistencies elsewhere, would be a major scientific achievement. So far, no proposed modification has succeeded in this goal. Early dark energy models improve the Hubble tension but worsen the S8 tension. Models with more complex dark energy properties can address some combinations of tensions, but typically require fine-tuning that reduces their appeal. The search for a clean, unified resolution continues. There is something intellectually interesting about the fact that all of these tensions point in the same direction, toward a universe that is observed to be expanding faster and with less pronounced structure than our best early universe-based predictions suggest. This consistency of direction across multiple independent observations is either a deep clue or a remarkable set of coincidences. The Occam's razor interpretation is that there is a single underlying cause, some modification to the cosmological model that shifts multiple predictions in the same direction simultaneously. What might that single cause be? One intriguing possibility involves the nature of dark matter itself. Current models treat dark matter as cold, meaning it consists of particles that were moving slowly at the time they were produced in the early universe, allowing them to cluster on small scales and form the dense halos in which galaxies are embedded. But there are variants of dark matter that are not perfectly cold. Warm, dark matter, consisting of lighter particles with higher initial velocities, would suppress the formation of small-scale structure. Interacting dark matter, which can exchange momentum with ordinary matter or with itself, would behave differently from cold dark matter in ways that affect both the expansion history and the clustering of galaxies. Some models even consider dark matter that decays over cosmic time into dark radiation, which would alter the energy budget of the universe in a direction that could help resolve the tensions. None of these alternatives to cold dark matter have been definitively confirmed observationally, but none have been definitively ruled out either. The search for direct evidence of dark matter particles in terrestrial experiments has so far come up empty. No dark matter particle has been detected in underground detectors, collider experiments, or indirect astrophysical observations. This absence of detection is pushing theorists toward a broader range of dark matter models, some of which have cosmological implications that could address the Hubble tension. The next generation of dark matter searches, including Xenont and Lux-Zeppelin for direct detection and the Cherenkov telescope array for indirect detection through gamma rays produced by dark matter annihilation, will probe dark matter properties at sensitivities beyond anything previously achieved. If dark matter is detected and its properties measured, it will immediately constrain which cosmological models are viable and could provide the key piece of information needed to resolve the Hubble tension. Science moves forward on multiple fronts simultaneously. While experimentalists build and operate the next generation of telescopes and detectors, theorists are constructing and testing new models. Computational cosmologists are running the largest simulations of cosmic structure formation ever attempted, using petascale supercomputers to model the evolution of billions of particles representing dark matter, dark energy, and ordinary matter from the Big Bang to the present. These simulations allow theorists to test whether proposed modifications to Lambda-CDM produce universes that look like the one we actually observe, not just in terms of the Hubble Constant, but across the full range of cosmological observables. The intersection of this theoretical work with the observational programs underway represents the current state of the art in cosmology. The field is large, international, and highly collaborative. A single major survey like the Dark Energy Spectroscopic Instrument involves hundreds of scientists from dozens of institutions across multiple countries. The papers that emerge from these collaborations represent thousands of person-years of expertise, carefully designed to extract the maximum possible scientific information from carefully gathered data. The fact that these efforts consistently find the Hubble tension rather than resolving it is a measure of both the quality of the science and the depth of the problem. We are living through an unusual moment in the history of physics. The two great theories of the 20th century, general relativity and quantum mechanics, each work extraordinarily well in their domains. But we do not have a complete theory that encompasses both. The standard models of particle physics and cosmology each describe their respective domains with impressive accuracy, but both have known gaps. Dark matter and dark energy, the dominant components of the universe by mass energy, are not explained by the standard model of particle physics. The matter-antimatter asymmetry of the universe, the reason there is any matter at all rather than an equal amount of antimatter, has no explanation within current theories. The Hubble tension may be one of several threads that, if pulled carefully, begins to unravel some of these deeper mysteries. Or it may turn out to have a more mundane explanation that leaves the existing framework intact. Either outcome would be valuable. If it is mundane, we learn something important about systematic biases in cosmological measurements. If it requires new physics, we gain the first empirical evidence for whatever that new physics is, and empirical evidence for new physics is the rarest. and most precious commodity in modern fundamental science, the history of human attempts to understand the cosmos is a history of repeatedly discovering that the universe is far larger, far more complex, and far stranger than we imagined. The ancient dome of stars became a solar system, which became one solar system among billions in a galaxy, which became one galaxy among hundreds of billions in an observable universe spanning 46 billion light-years in every direction. At each step, the revision in scale was accompanied by a revision in understanding. New physics, new concepts, new mathematical frameworks. The Hubble tension may be announcing the next step. We do not yet know what it will reveal, but the instruments are running. The data is accumulating, the theorists are calculating, and the answer is out there, encoded in the light of ancient stars and the microwave glow of the early universe, waiting to be read correctly. That is the situation cosmology finds itself in today, and it is one of the most intellectually compelling situations in the history of science. To fully appreciate the Hubble tension, it helps to understand just how the two camps arrived at their numbers, and why astronomers have spent so much energy trying to find flaws in each other's methods. The distance ladder approach has been refined over many decades, but its fundamental vulnerability is that each rung introduces potential calibration errors that propagate to the next rung. If the Cepheid period luminosity relationship is slightly different in the galaxies being used to calibrate type Ia supernovae than it was in the calibration sample, then the distances to those supernovae will be slightly wrong, and the Hubble constant derived from them will be slightly wrong. Similarly, if the intrinsic peak brightness of type Ia supernovae varies in some systematic way with the environment or metallicity of the host galaxy, then those supernovae are not the perfectly uniform standard candles we treat them as. These potential biases have been studied extensively. The Cepheid distance scale has been cross-checked with geometric distance measurements to the Large Magellanic Cloud, obtained from eclipsing binary star systems with known orbital properties. The type Ia supernova brightness standardization has been refined using machine learning algorithms that identify the subtle correlations between supernova light curve shapes, colors, and their host galaxies' stellar populations. The result of all this scrutiny has been to make the high value more robust, not less. Each time a potential systematic bias is identified and corrected, the resulting Hubble constant ends up roughly the same, around 73 kilometers per second per megaparsec. The cosmic microwave background analysis faces its own potential pitfalls. The microwave sky is not just cosmic background radiation. It also contains foreground emission from the Milky Way, from other galaxies, and from clusters of galaxies that can distort the background signal through a process called the Sunyaev-Zeldovich effect, in which hot electrons in galaxy clusters scatter background photons to higher energies. Removing these foregrounds accurately is an enormous technical challenge. The Planck team has developed sophisticated methods for foreground separation using multiple frequency bands to distinguish the characteristic spectral signatures of different emission sources. But if any foreground component is not fully removed, it could bias the inferred cosmological parameters. Critics of the early universe measurement have pointed to specific features in the Planck data that could indicate residual foreground contamination. Defenders of the Planck results have argued that these features are statistically insignificant and that the results are robust against multiple independent analysis choices. This scientific back and forth is the normal process by which major results get tested and refined. It is not a sign of weakness in cosmology, but of the rigor with which the community scrutinizes its most important findings. The upcoming CMB-S4 experiment and the Simons Observatory will provide ground-based measurements of the microwave background with sensitivities that in some frequency ranges will rival or exceed Planck's. Because they operate from the ground, they observe through the atmosphere, which itself emits and absorbs microwave radiation, making certain types of measurements more challenging. But for angular scales smaller than about 1 degree, ground-based telescopes can achieve exceptional precision in measuring the fine-scale structure of the cosmic. Microwave background temperature and polarization at these scales provides additional cosmological information beyond what Planck's full sky maps have already extracted. These measurements will constrain the cosmological parameters independently of Planck and either confirm or challenge its Hubble constant prediction, one of the most promising near-term developments. in resolving the Hubble tension involves measuring the absolute distances to more galaxies using geometric methods that do not rely on any physical calibration assumptions. Beyond megamasers, which have provided a handful of such measurements so far, there are techniques based on the statistics of gravitational lensing, the bending of light from a background source by a foreground mass that can, in principle, yield geometric distances to lensing systems billions of light-years away. The H0 Licao and TD Cosmo collaborations have used this approach, measuring the time delays between multiple images of a background quasar created by gravitational lensing from a foreground galaxy. Because the multiple images travel slightly different path lengths through spacetime, they arrive at slightly different times. The ratio of the time delay to the path difference depends on the Hubble constant, allowing it to be extracted from careful modeling of the lens system. This time delay cosmography approach has yielded Hubble constant values around 73 kilometers per second per megaparsec, consistent with other late universe measurements. However, the method requires an accurate model of the mass distribution of the lensing galaxy, and there has been debate about whether the freedom in this mass model introduces a systematic bias called the mass sheet degeneracy. When this degeneracy is accounted for more conservatively, the resulting Hubble constant values shift downward and the uncertainties increase. This illustrates the general theme. Every method has potential systematic effects that must be carefully characterized, and the more carefully they are characterized, the more credible the resulting measurement. The way forward is not to argue about which method is right in the abstract, but to collect enough measurements from enough independent methods that the systematic biases of any individual approach are diluted by the collective weight of the evidence. This is why the diversity of the high-value measurements, Cepheids, supernovae, megamasers, Mira variables, gravitational lensing time delays, is so significant. No single one of these methods is perfect, but when all of them return values clustered around the same number, and that number consistently differs from the early universe prediction, the burden of proof shifts toward finding a flaw in the cosmological model rather than in all the independent measurements. Simultaneously, the interplay between different cosmological probes also creates opportunities for cross-checks that were not possible a generation ago. The Baryon Oscillation Spectroscopic Survey and its successor, the Dark Energy Spectroscopic Instrument, have measured the Hubble constant using a technique called baryon acoustic oscillations. In the early universe, before the cosmic microwave background was released, the hot plasma was compressed in some regions and rarefied in others. Pressure waves, acoustic waves, propagated through this plasma, moving outward at the speed of sound in a relativistic fluid. When the universe cooled enough for atoms to form and the plasma became neutral, these waves froze in place, leaving a characteristic scale imprinted on the distribution of matter. That scale, roughly 500 million light-years, has been expanding with the universe ever since, and it is visible today as a small but detectable excess in the probability of finding two galaxies separated by that distance, because the baryon acoustic oscillation scale was set by well-understood physics in the early universe. It provides a standard ruler, a known physical length that can be used to measure distances across the universe by comparing its apparent size to its known actual size. This approach depends on the early universe calibration of the sound horizon scale, which ties it to the cosmic microwave background analysis. The resulting Hubble constant from baryon acoustic oscillations is therefore closer to the early universe value, around 67 to 68 kilometers per second per megaparsec, which is consistent with the idea that both methods are measuring the same underlying model, but this also means that the discrepancy between early universe and late universe methods is not just between the cosmic microwave background and the distance ladder. It is between any probe that uses early universe physics as its calibration anchor and any probe that directly measures the current expansion without relying on that calibration. The dichotomy is fundamental, not methodological. This is why many cosmologists believe the resolution requires changing the physics, not just improving the measurements. Dark energy is the most natural candidate for modification. Because it is the least understood component of the cosmological model, we know dark energy exists. The supernova surveys in the 1990s proved it conclusively, but we know almost nothing about what it is at a fundamental level. The simplest model is a cosmological constant, a constant energy density of empty space, perfectly uniform and unchanging. This model fits all current observations well, with the notable exception of the Hubble tension. If dark energy is instead a dynamical field, something that varies in time and space, similar to other known fields in physics, then its behavior could differ between the early and current universe in ways that naturally produce a higher observed expansion rate today than the early universe models predicted the dark energy. Spectroscopic instruments' first results, released in 2024, provided tantalizing hints of dynamic dark energy, a dark energy equation of state that deviates from the cosmological constant value of -1. The statistical significance of these hints is around 2 sigma, which is suggestive but not conclusive. Follow-up analyses with more data will test whether this deviation is real or a statistical fluctuation. If confirmed at higher significance, it would represent the first empirical evidence that dark energy is not a cosmological constant, a discovery that would transform cosmology and win multiple Nobel Prizes. The universe has a way of revealing its deepest secrets only when our instruments become sensitive enough to detect them. The discovery that the expansion is accelerating was made possible by the Hubble Space Telescope and the large CCD detectors that became available in the 1990s. The detailed mapping of the cosmic microwave background was made possible by dedicated space missions with advanced cryogenic detector technology. The detection of gravitational waves was made possible by kilometer-scale laser interferometers so sensitive that they could detect a displacement 1,000th the diameter of a proton. The resolution of the Hubble tension will likewise require instruments of extraordinary capability, and many of those instruments are now under construction or already observing. The next decade represents a convergence of technological readiness and scientific urgency that occurs rarely in any field. We are asking the right questions at a moment when we are finally building the tools capable of answering them. The universe began approximately 13.8 billion years ago in a state of extraordinary density and temperature. In the first fraction of a second, the fundamental forces separated, quarks combined into protons and neutrons, and the physical laws that govern all subsequent evolution were established. Over the next few 100,000 years, the universe cooled enough for atoms to form and release the light we now observe as the cosmic microwave background. Over billions of years, matter clumped under gravity to form galaxies and galaxy clusters, while dark energy drove the expansion to accelerate. Today, 13.8 billion years later, one species on one small planet in one galaxy among hundreds of billions has developed the ability to measure how fast the universe is expanding, and has found that 2 independent measurements of that rate disagree. That disagreement is not an endpoint. It is the beginning of a question whose answer will tell us something about the universe that no one yet knows. The measurement that finally resolves the Hubble tension, whatever it turns out to be, will take its place in the history of astronomy alongside Hubble's Cepheid in Andromeda, Penzias and Wilson's microwave noise, and the supernova team's discovery of accelerating expansion. It will mark the moment when a long-standing anomaly yielded its secret, and the picture of the cosmos became a little clearer, a little stranger, and a little more complete. If you have stayed with this story to the end, you already understand something important: that science at the frontier is not a collection of settled answers, but an ongoing confrontation with what we do not know. The Hubble tension is one of the most precisely characterized mysteries in modern physics. It has been measured from multiple directions, probed with multiple independent methods, and it refuses to disappear. It is real, it is significant, and it is telling us something. Figuring out what it is telling us is one of the most important tasks in science today. The next finding could come any time, from the next batch of gravitational wave detections, from the next release of dark energy spectroscopic instrument data, from a more detailed analysis of the rotating universe model, or from some entirely new direction that no one has yet considered. The cosmos does not reveal its secrets on a schedule, but it does reveal them to those patient and precise enough to keep looking. There is one more dimension of the Hubble tension that rarely gets discussed in popular science coverage, and it concerns the nature of scientific certainty itself. When we say the Hubble tension exists at 5 sigma statistical significance, we are making a statement about probability and specifically about the probability that the observed discrepancy could arise by chance from measurement noise alone. 5 sigma means that probability is about 1 in 3.5 million. By conventional scientific standards, that is overwhelming evidence that the discrepancy is real. But statistical significance and scientific truth are not the same thing. Statistical significance tells us that the data is inconsistent with a particular null hypothesis. In this case, the hypothesis that both methods are measuring the same true Hubble constant, and the apparent difference is just random noise. It does not tell us which measurement is closer to the truth, or why they differ, or what physics is responsible. A 5 sigma discrepancy that is caused by a subtle systematic bias in one of the measurement pipelines is just as statistically significant as one caused by genuine new physics. The statistics alone cannot distinguish between these possibilities. This is why cosmologists have invested so heavily in diversifying the measurement methods. By measuring the Hubble constant with Cepheids, and then confirming the result with supernovae, and then confirming again with megamasers, and then again with Mira variables, and then again with gravitational wave standard sirens and lensing time delays, scientists are building a case that is not just statistically significant, but robust against the specific systematic biases of any individual technique. The convergence of independent measurements toward the high value is qualitatively different from a single highly precise measurement, precisely because it cannot be explained by any single systematic effect. The cosmic microwave background result also comes from multiple independent analyses. The Planck team's official results have been cross-checked by independent groups using different analysis pipelines, different foreground models, and different statistical methods. The ACIT and SPT ground-based experiments have measured the small-scale microwave background independently and obtained results consistent with Planck's cosmological parameters. The low value of the Hubble constant from early universe methods is not dependent on Planck alone. The tension is therefore not between two single measurements. It is between two robust bodies of evidence, each supported by multiple independent approaches that consistently point to different numbers. That is what makes it genuinely difficult and genuinely interesting. Consider the historical parallel with the neutrino. In the 1930s, physicists studying radioactive beta decay noticed that energy seemed to disappear during the process. The total energy of the products of a beta decay reaction was consistently less than the energy of the original nucleus. By the law of conservation of energy, one of the most fundamental principles in physics, this was impossible. Something was carrying away the missing energy. Wolfgang Pauli proposed in 1930 that a tiny neutral particle was being emitted in the decay, carrying energy without being detected by any existing instrument. He called it a neutron at first. Enrico Fermi later renamed it the neutrino. For 26 years, the neutrino was a theoretical entity with no direct experimental confirmation. It was inferred purely from the energy discrepancy in beta decay. In 1956, Clyde Cowan and Frederick Rains finally detected neutrinos directly, using a nuclear reactor as a source. The missing energy had been real all along, and the particle carrying it away had been hiding below the detection threshold of earlier experiments. The Hubble tension may be announcing something similar. A missing element in our cosmological model that, once identified and incorporated, will make both measurements consistent. The missing element might be a new particle, a new field, a new property of space-time, or a modification to how we describe dark energy or dark matter. Whatever it is real enough to show up consistently across multiple independent measurements, which means it has observable consequences that future experiments are capable of detecting. The analogy is not perfect, the neutrino solution to the energy discrepancy was clear and clean once the particle was detected, while the Hubble tension is embedded in a much more complex system of interconnected physics. But the intellectual structure is similar, a precise discrepancy between measurement and theory, persistent across multiple tests, pointing towards something the theory is missing. There is also the possibility, which should not be dismissed, that both sets of measurements are correct, and the discrepancy arises because we are incorrectly assuming that the Hubble constant is a single number. If the universe is not perfectly uniform on the largest scales, if there are genuine large-scale variations in the density of matter that cause different regions to expand at slightly different rates, then what we call the Hubble constant is actually an Average over different local expansion rates. Measurements based on objects within our cosmic neighborhood might give a different average than measurements based on the early universe, not because either is wrong, but because they are sampling different averages of a quantity that varies in space. This idea has been explored under various names, including cosmic variance and local bulk flows. The Milky Way and surrounding galaxies are known to be moving with a particular velocity with respect to the cosmic microwave background rest frame, a bulk flow of several hundred kilometers per second in a specific direction. If this bulk flow is part of a larger coherent motion driven by large-scale matter distribution, then our local universe is not a perfectly representative sample of the cosmos as a whole. The question is whether these local effects are large enough to explain the entire Hubble tension. Current estimates suggest they are not sure. The discrepancy is too large to be attributed entirely to cosmic variance or local bulk flows. But these effects probably contribute at some level, and disentangling their contribution from the primary source of the tension requires careful statistical analysis of how the measured Hubble constant varies as a function of which objects are included in the sample and at what distances. This is precisely the kind of detailed, systematic analysis that the next generation of surveys will enable. With millions of supernovae, hundreds of millions of galaxy redshifts, and precise weak gravitational lensing maps covering a significant fraction of the sky, future surveys will be able to test the isotropy and homogeneity of the universe at levels of precision far beyond what is currently possible. If there are large-scale variations in the expansion rate, they will show up as angular dependence in the measured Hubble constant, different values in different directions on the sky. This would be a striking and unambiguous signal that the universe is not as uniform as our cosmological principle assumes. Whether or not such variations are found, the data from these surveys will transform our understanding of dark energy, dark matter, and the large-scale structure of the cosmos. They are being designed and built not just to resolve the Hubble tension, but to address the full spectrum of outstanding questions in cosmology: the nature of dark energy, the properties of dark matter, the growth rate of cosmic structure, the total mass of neutrinos, the validity of general relativity on cosmological scales. The Hubble tension is one node in this rich scientific network, connected to all of the others. This interconnectedness is what makes cosmology at the current moment so fertile. Resolving one tension often provides constraints that reduce uncertainty in several others. Finding the correct model for dark energy fixes the Hubble tension, constrains the S8 tension, and determines the fate of the universe. Finding the correct model for dark matter explains the structure of galaxies, the properties of galaxy clusters, and the abundance of small satellite galaxies. Each piece fits with all the others, which means that getting any one piece right advances the whole picture. The universe is approximately 93 billion light-years across in diameter, the part we can observe, bounded by the horizon beyond which light has not had time to reach us since the Big Bang. Within this sphere are roughly 2 trillion galaxies, each containing hundreds of billions of stars. The total number of stars in the observable universe is approximately 100 billion trillion, a number so large that counting them at a rate of 1 per second would take 10,000 times the current age of the universe. The Milky Way alone contains something between 100 and 400 billion stars, and our Sun is a thoroughly ordinary one among them. Against this backdrop of cosmic enormity, the Hubble tension is a disagreement of 6 kilometers per second per megaparsec, a tiny number in absolute terms, but enormous in its implications. It tells us that across the observable universe, for every 3.26 million light-years of space between any 2 points, those points are moving apart at a rate that is either 67 or 73 kilometers per second, and we do not know which. Or more precisely, both measurements are right, and the disagreement is telling us that something about how the universe has expanded over its history differs from what our best model predicts. That small number contains, possibly, the seeds of a revision to our deepest understanding of physics. The history of science suggests that when measurements persistently disagree with theory, nature is usually trying to tell us something. The Hubble tension has been whispering that message for over a decade, with growing insistence. The next chapter of cosmology will be about learning to listen more carefully, with better instruments, sharper theories, and the willingness to revise even our most foundational assumptions about the universe we inhabit. We began with Hubble's discovery that the universe is expanding. That single observation, made by one astronomer with one telescope in 1929, opened a century of inquiry into the nature, origin, and fate of the cosmos. Today, nearly 100 years later, the rate of that expansion, the Hubble Constant, stands at the center of the most consequential open question in modern cosmology. The resolution, when it comes, will be worthy of the question. The universe is under no obligation to fit neatly into our models, but it is generous enough to leave clues. In the redshift of ancient light, in the pattern of microwaves from the infant cosmos, in the precise timing of gravitational waves from colliding stars. Learning to read those clues correctly is what science does. And right now, science is reading as carefully as it ever has.